there's lots of them. What if there were more of them? What if there are a lot more of them? This is a claim that some physicists like to make. But why? Before we go answering this question, let's start off with a different question. What is a particle? When we're talking about particles in physics, we're usually talking about stuff that's smaller than atoms. There are two types of particles, fundamental particles and composite particles. Fundamental particles are the smallest bit of stuff we know about. Composite particles are a bunch of fundamental particles called quarks in a trench coat. There are two types of composite particles called baryons and mesons. Physicists describe fundamental particles as collapsed wave functions, quantum excitations of a field, irreducible representations of a Poincare group, or other fancy descriptions. For the purpose of this video, just think of them as all the smallest things that make up everything. Right now, we know of at least 36 fundamental particles, but we didn't always know about all of them. In fact, we didn't really know about any particles until the end of the 19th century. If we didn't know about those, who's to say there aren't more? So why not just add a few more? That's what theoretical physicists like to do. Those who propose a bunch of whimsical names for particles they just made up, like
SUSY
Particles, WIMPs, and Gravitons. But before we embrace these silly little guys, let's take a look back at a bunch of particles we know exist and figure out what motivated scientists to theorize their existence and how they were discovered. Then, we can compare currently theorized particles to them. To the time machine! The year is 1897. At this point, scientists know about atoms, elements, and all that jazz, but they really don't know what these atoms look like. However, a year ago, they discovered this really cool thing called radiation, which seems to be related to atoms. So a lot of scientists are having safe, wholesome fun playing with it. Enter J.J. Thomson. He's interested in glowing tubes and wants to know how they work. So, he performs a bunch of experiments to learn about the pretty lights, or cathode rays as fancy people call them. And after playing with the lights and exposing them to magnets, JJ announces to the scientific world, "Hey, these pretty lights are charged particles. Also, atoms are just pudding with a bunch of these bad boys in it. Also, I'm going to call these particles corpuscles." Pfft, corpuscles are a stupid name, we're just going to call them electrons. But that's cool. Later on, one of JJ's students, Ernest Rutherford, takes over. He loves playing with radiation, and by this point, scientists have identified three types of radiation: alpha rays, beta rays, and gamma rays. These are just fancy names for helium atoms, electrons, and photons. Ernie thinks that radiation is caused by the breakdown of atoms. In 1911, Ernie uses gold to determine that atoms are not actually pudding. Instead, atoms have this positively charged center, or nucleus, and a bunch of electrons orbiting it. But no one really knows what it's made of. 8 years later, Ernie's playing with radiation and figures out if you shoot helium atoms at a nitrogen atom, you get what he thought was a hydrogen atom. But later, he realizes that these aren't quite hydrogen atoms, but instead just the center of hydrogen atoms, which he called a proton. So, Ernie announced to the scientific world, "Hey, the nucleus of the atom is actually made of a bunch of protons." Hey, that's not a bad name. Also, these protons are pretty neat, but a helium nucleus has twice the charge of a proton, and more than 4 times the proton's mass. What gives? So now we have a pretty good idea of what the atom looks like. But we still have this lingering question about the mass of the nucleus. That's where our next particle comes in. Ernie didn't know where this extra mass came from, but he theorized the extra mass may come from protons and electrons fused together to form a new particle, but really didn't have any proof. Then, one of Ernie's former students, James Chadwick, came back from Germany to work with Ernie. Jimmy had left to Germany to work with Hans Geiger, but instead just spent the last 4 years playing with radioactive toothpaste in a prison camp because some dude with a mustache got shot in Austria. The question of what gives the nucleus extra mass but no charge puzzled Jimmy, as he worked on his other research projects like studying beta decay. Then, in 1932, Jimmy became interested in the work of a bunch of scientists who were shooting helium atoms they got from polonium at a beryllium atom. Those scientists thought this radiation was photons, but Jimmy figured out that the radiation the beryllium atoms produce actually had a little bit more mass than the protons after shooting this radiation at a bunch of different atoms. So Jimmy told the scientific community, "Hey guys, maybe this radiation isn't photons, but instead those neutral particles Ernie was talking about? Maybe, I don't know. Also, can we call them neutrons?" What? I said that radiation is neutrons, not photons. Also, look what I can do. I personally think neutrons are pretty cool. Here, let me just... Yeah. Go, neutrons, be free! Enjoy your life away from the cruel confines of your atomic prison!
Yippee!
I love that little guy. I sure hope nothing bad happens to him in 14 minutes and 39.6 seconds. So, It's 1905, and there's this dude named Albert Einstein, and he says, hey, light's pretty cool, let me just break physics for you, and introduce special and general relativity. Then, in 1926, Schrödinger and Heisenberg said, atoms are pretty cool, let's just break physics for you, and introduce quantum mechanics. These two theories each explained a lot of things, but they didn't really mix. So, in 1928, some dude whose name I forget said, hey, what if I combine quantum mechanics and relativity? And so he did. He made this equation, did some math, and got negative energy. But instead of admitting his mistake and crying in the shower of your repeated failures and growing dread that your mother was right and you'll never amount to anything, like the rest of us, he doubled down and said, nah, actually fermions have curly brackets. And thus, the theory of antiparticles was born. What's his name theorized these antiparticles were identical in every way to regular particles except that they had opposite charge. This theory was founded on a concept called charge conjugation, which is the idea that nothing really changes if you invert the charge of everything. 4 years later, Carl Anderson observed the positron, the antiparticle to the electron, while studying cosmic ray showers in a cloud chamber. He noticed that the tracks left by some particles in his cloud chamber had the same mass but opposite charge as the electron. And so, antiparticles were confirmed, and everyone won a Nobel Prize. Remember our friends Jimmy and Ernie? Well, Ernie and a bunch of other scientists were playing with alpha, beta, and gamma rays. They noticed that alpha and gamma rays always had a distinct energy. Nice! But in 1914, Jimmy found out that the energy levels of beta rays were continuous. This seemed to violate conservation of energy. Weird. Fast forward to 1930, and Wolfgang Pauli comes along and says, Dear radioactive ladies and gentlemen, energy is conserved. What if there was this neutral, lightweight particle that is very weakly interacting and almost impossible to observe? Since they are neutral particles, I shall call them neutrons. Then Jimmy came along and stole the name neutron for his particle, so this other dude, Enrico Fermi, renamed Paul's particle to neutrino, meaning little neutral one, and said, hey, what if there was this weak force that kills neutrons and leaves protons, electrons, and antineutrinos as evidence? Luckily for us, Jimmy has been working on this cool source for a bunch of neutrons. Maybe let's not do that. Let's use this instead. So a team of scientists led by Los Alamos National Lab physicists Frederick Raines and Clyde Cohen set up a 10-ton liquid scintillator placed next to a fission reactor at the Savannah River plant. They named this project Project Poltergeist because neutrinos are hard to detect, just like ghosts are in real life. They hoped that the neutrinos would react to the protons in the detector and undergo reverse beta decay, and lo and behold, it did. Neutrinos have a bunch of other problems scientists wouldn't solve until later, but now we know that they exist. Fast forward a bit. We've discovered a bunch of particles and a bunch of forces they interact with, and some of these forces seem to be related. Nice. Let's put them into a model. Nice. But to build this model, we had to use fancy math tricks, and that implies our force carriers, these guys, are massless. But these ones aren't massless. What gives? So in 1964, these three nerds, Robert Brout, Francois-Englert, and Peter Higgs, think they have a solution. See, our model was built on a bunch of fields and symmetries, so they introduced a new field that gave bosons mass, but this new field would have to break symmetry, so they introduced a new trick. We want our equation to be symmetric, but the massive bosons seem to break symmetry. So, they claimed at the Big Bang, this new field was symmetric, but unstable. So right after the Big Bang, the field found a stable state which broke the initial symmetry and gave the W and Z bosons mass. They named this new field the Higgs field after this one. Great, we fix our problem, but in the process we create a new particle. You see, whenever we introduce a field, it creates a new particle. The particle to the Higgs field is called the Higgs boson. This model predicts that it has no spin, no charge, and doesn't interact via the strong force. Also, it's super massive, so it's going to take a lot of energy to find it. Good luck.
One eternity later.
It's 2008, and a bunch of scientists built this really big circle we can use to slap particles together with a lot of energy. They've also figured out models for how to produce the Higgs boson and how it decays. So, after slapping a bunch of particles together, in 2012 they gathered enough data to prove the existence of the Higgs boson. This announcement was met with much fanfare. Cool. So now that we have an understanding of how we theorize and discover new particles, let's travel back to the present. To the time machine! Ugh, it reeks in there. Anyway, so now you have an idea of how physicists predict new particles. Physicists say to themselves, hey, I have a problem. If I make up a particle, I fix this problem. This is how the particle I made up should look like. Here's an experimental result we would expect to see if this particle existed. They didn't always follow this process early on, but as physicists search for more and more exotic particles, this 4-step process becomes the only reliable way to find new particles. So, with these 4 points in mind, let's look at currently suggested theoretical particles. The first theoretical particle on our list is the graviton. So, our standard model is pretty cool. It explains electromagnetism, the strong force, and the weak force. In the standard model, these three forces are mediated by the bosons. However, there are four forces, not three. Where's gravity? Unfortunately, the fact that the standard model doesn't account for gravity doesn't mean you Australians can take off your ground harnesses quite yet. Theoretical physicists made up a particle for gravity called the graviton. The idea that gravity was mediated by a particle was actually originally thought up by Pierre-Simon Laplace. Yeah, that Laplace. But he didn't really have the same understanding of this particle as we do today. Like the photon, the graviton would be massless and have no charge. General relativity also somehow tells us that the graviton must have spin too. Great, so why can't we detect it? Well, gravity is much weaker than all the other forces, which would make interactions from the graviton really hard to detect. This leads some theorists to predict that gravity operates in more than our usual 3 dimensions, and so is spread thinner than the other forces. What does this extra dimension look like? Physicists like to describe it as a tightrope. A human can only walk forward and backwards, but an ant can walk all the way around the tightrope. So, physicists look for the graviton by looking for these small dimensions. They do this by looking for particles that are more massive than our standard particles, but with all the other properties the same. These are called Kaluza-Klein states. These states have been looked for at the big circle that found the Higgs. However, Kaluza-Klein states have not been found. The search for extra dimensions continue, but until then, the existence of the graviton remains a mystery. So, we have our standard model with all its symmetries and fields, and we've got our Higgs field, which gives all the other particles mass. However, whenever the other particles couple to the Higgs field, the mass of the Higgs boson, which we represent as the Higgs squared mass, receives this correction. The problem is, this value is pretty big. And this value is this for the top quark, which is the most massive fundamental particle, so has the largest correction. If we do this maths, that gives us that this Higgs squared mass is some 30 orders of magnitude greater than what we'd expect using the standard model as an effective field theory. An effective field theory is just a fancy way physicists like to say approximation. But this is not good. This problem is known as the hierarchy problem. In essence, why is this number so much different than this number? Now, it's possible that these other values in the expansion happen to cancel, but this doesn't seem natural and makes the Higgs potential sensitive to new theories. So, physicists looked elsewhere. Julius West and Bruno Zumino came up with this idea called supersymmetry. Supersymmetry is the symmetry between fermions and bosons. This gives all our particles what are known as superpartners, which differ from our original particles by a spin of 1/2. This changes our correction to this, which fixes our original problem. This theory also unifies all the forces in the early universe and predicts something called a WIMP, which is a potential dark matter candidate we will discuss later. This theory would affect the rates of certain interactions, so we tried to detect these different rates in the big circle. However, these different rates have not been found at the energies that the big circle operates at. The existence of the gluino, the supersymmetric partner to the gluon, has been ruled out up to the mass of 2 tera-electron-volts. Some theorists hope that it will appear at higher energies, or that there is some reason they have escaped detection, because it's a really nice theory, but so far, we don't have any real proof yet. While I get the appeal, the fact that no evidence has appeared yet makes me think that supersymmetry is pretty SUSY. Wait, what do you mean it's pronounced SUSY? So, galaxies. They're pretty cool. A bunch of scientists noticed that galaxies are spinning faster than their visible mass suggests they should. This indicates that there's mass which we can't see. Physicists call this dark matter. This dark matter apparently makes up 27% of the universe, way more than the 5% from normal matter. Since we can't see dark matter, we know it doesn't interact with photons, so we know it's not charged. We also know it doesn't interact through the strong force because it doesn't interact with cosmic rays. We don't know about the weak force, but we can't detect it if it only interacts with gravity, so let's hope it interacts through the weak force. So there we have it, the weakly interacting massive particle, or WIMP. As I mentioned earlier, the WIMP is predicted by supersymmetry. This is called the WIMP miracle, since it was an indirect result of supersymmetry, and it gave theorists hope that the WIMP existed. Since they interact through the weak force, physicists believe that we could detect them if they collide with particles like quarks, which couple to the W and Z boson. Since quarks make up protons and neutrons, we should be able to see nuclear recoil from WIMPs. This recoil could be detected and used as proof for WIMPs. However, physicists have not seen this recoil beyond what we would expect by other background noise. In fact, the results have ruled out many previous models of SUSY dark matter, so, as of yet, WIMPs don't seem to exist. There are many more theoretical particles, like tachyons, which move faster than the speed of light, or inflatons, which explain why our universe expanded right after the Big Bang. Unfortunately, we don't have time to explore them all, but the story for all the current theorized particles is the same. They solve a problem, they create a particle, the particle will have predicted properties, but we don't have any experimental proof for any of them. Theorists can tweak the models all they want, but in the end, until it produces experimental results, they're just whimsical ideas. This has been Physics. Thank you for watching.